Hi, my name is Jinhyun Park, and today I'm gonna have a brief presentation about the geometry of the reactor. I mean, the shape of the reactor. So, this is the contents we will cover today. So let's get started. So far, in our chemical reaction engineering class this semester, we have learned about various types of the reactors, such as batch and semi-batch reactor, CSTR, PFR, and PBR. However, studying these reactors, I noticed that they are all cylindrical or tubular. So, I just wondered if we can use other geometries for reactor. Obviously, we can easily imagine other geometries for reactor, such as trigonal prism, sphere, or cuboid as shown here. Then, why don't we use or learn them in class? Don't you wonder? So today, we are gonna take a look at the geometry of the reactor. First of all, it is very easy to notice that we cannot adopt angled geometry such as trigonal prism or cuboid. The reason is quite obvious, and that's because their angles introduce a large amount of friction to reactant flow, and thus resulting in larger pressure drop and lower conversion. It's quite obvious, right? So, there is no need for us to use such reactors even if it is possible. However, unlike other geometries, engineers have figured out that spherical reactor is much more efficient than conventional reactors such as PFR or PBR. So, from now on, we are gonna see the reason why spherical reactor is more efficient. To briefly explain, as I said right before, spherical reactor introduces only small amount of pressure drop for reactor, and thus it has a higher conversion than traditional reactors. Why? To briefly explain, let's take a look at this picture. Here, we can see that spherical reactor can provide much larger mean cross-sectional area and smaller distance of travel for flow compared to traditional PFR or PBR. Also, if we consider this Argon equation, we can easily notice that pressure drop will be significantly reduced if we decrease g, the superficial mass velocity. Here, as shown in the picture, g is the ratio of mass flow rate over cross-sectional area. So, with larger cross-sectional area, much less pressure drop will occur. It's obvious, right? And furthermore, spherical reactor is better for the cost as well. As shown in this picture, we can make much larger feed rate for spherical reactor compared to traditional PFR. So, that would clearly lower the manufacturing cost since we don't have to perform small processes over and over again. Only one large process will be enough since we have higher feed rate at once, and that will be clearly cheaper than before. And also, since there's only negligible amount of pressure drop, we don't need any additional pump or turbine. Therefore, we don't need to pay for additional equipment, right? Okay. Then from now on, let's take a look at the quantitative explanation with from reactant A to product B reaction. First, the mole balance of spherical reactor is very similar with that of PFR. In minus out plus generation equals 0 for steady state. And the result is as follows. And taking derivatives, we get this mole balance equation, and in terms of conversion x, we can get this design equation. It's very obvious since we have learned it in preceding chapters in this class. Right? And then, now the ratio of spherical packed bed reactor is as follows. And assuming isothermal condition and gas phase reaction, we can express stoichiometry in this way. Here, y indicates pressure drop P over P0. And this stoichiometry expression is very obvious since we have learned it in maybe chapter 4. Then with this Argon equation, since y equals P over P0 and dy equals dP over P0, we can express Argon equation in this way. So it has a new form. And here, as we have learned in chapter 5, beta 0 can be expressed in this way. And again, here G is the ratio of mass flow rate over cross-sectional area. So now, what I want to do is to express G with many variables such as reactor area or reactor volume to relate G more directly to the pressure drop. So considering this picture, here R is the radius of the sphere, that is the length from the bottom line to the center of the sphere, and Z is the length from the bottom line to the area we are interested in. So with this derivation and picture, we can express the area A like this. Then the volume can be calculated by taking integral like this. And as a result, the catalyst weight W, which is the product of catalyst volume and density, can be calculated like this. As a result, with these expressions, we can modify beta 0 and finally Argon equation so that they can be expressed with respect to the area or volume of the reactor. And that will make us able to quantitatively explain the reduced pressure drop in spherical reactor, right? And finally, we combine all these information about balance, rate law, stoichiometry, and pressure drop with polymath. We use polymath or other computer software or programs since we can't simply combine and calculate it with our own hands. It's too much complicated. Here, I'm not gonna show you the detailed polymath code or calculation because they are too complex, but with the result gotten by polymath, we can clearly see that the conversion is higher when we use spherical reactor than when we use PFR or PBR at the same condition. So, considering its efficiency, there is no doubt that spherical reactor has many industrial applications, especially for large processes. To show you one of the most typical examples, spherical reactors are used at a petrochemistry plant, as shown here. And so let me show you some pictures of such an example. See? Many companies use spherical reactors to reform naphtha or produce fuels like petroleum. And also, since higher feed rate is possible, it is used for the mass production of polymers in polymerization processes. And furthermore, there are many papers about the use of spherical reactor for nuclear power plant. So, there are so many uses and applications of spherical reactor, right? So let's move on to our final part, conclusion. This is the reference that I referred to for this presentation. Okay. So in conclusion, clearly there are lots of possible geometries for reactor other than what we have seen and learned in class. And among them, spherical reactor is more efficient than other types of traditional reactors for both cost and conversion. So it's much more efficient than other traditional reactors. And therefore, these days, spherical reactor is in use in many industries. That's quite obvious. So this is the end of my presentation, and thank you for listening.